Okay, homework 10, problem 1. Problem 1 gives us a Poisson process where random variable n, when the probability of random variable n in this interval equals k is given by this Poisson equation. So the first part asks us to find expected value of x of t. Well, what's x of t? X of t is this. It's n evaluated on the interval from 0 to t. So let's find expected value of x of t. It's very similar to finding the expected value of just a regular Poisson distribution. So we start off with e lambda t is equal to, this is just the expansion of e. Start with this. And what I'm going to call lambda t equal to alpha. I'm going to just call lambda t alpha. So I have e to the alpha summation k from 0 to infinity of alpha k over k factorial. So then what I do is I take the derivative with respect to alpha on both sides. So on here you just get e to the alpha. On this side you get k alpha k minus 1 over k factorial. K goes from 0 to infinity. Let's see. And we have... right, this is right. Okay. So we have alpha to the k minus 1, so I can rewrite that as k over alpha to the k over k factorial. Right, so at k equal to 0, we just get 0, so we can literally just start the summation from 1 and go onward, because if we start at 0, it's the same thing, because at 0 this becomes 0. Now the alpha we can take out, because it's a constant, so we get 1 over alpha summation k alpha to the k over k factorial from k equals 1 to infinity. So what I'm gonna move the alpha, so this is equal to e to the alpha. So I'm gonna move the alpha here and move the exponential on the other side. So I get alpha equals, I'll put this exponential in the summation. We have k e to the minus alpha k over k factorial. K goes from 1 to infinity. This thing just looks like the Poisson process times k, and it's and doing the sum. So this is the expected value of x of t. Now what's alpha? It's just lambda t. So the expected value of x of t is just lambda of t. Okay. Now part B wants the autocorrelation. So start with B, autocorrelation. So by definition, autocorrelation is equal to expected value of xt1, xt2. Now we can use a bit of a trick. So for here, I'm gonna use the condition that t2 is greater than t1. We're going to come back to this. I'm just going to assume this for now, and then we're going to explain why it's important. So we can rewrite x of t1, x of t2 as this. Minus xt1, xt1, right? We can rewrite it as this. So we're going to plug that into the expected value. So r of t1, t2 is equal to expected value of, I'm going to just start dropping these little vectors, but just know that it's a random variable, it's capital. So we have this times this. So I'm going to multiply through. So we get expected value of x of t1 times x of t2 minus x of t1 plus x squared of t1. So basically what I did, I took this as a separate piece of the sum, multiplied that by that, and then I just multiplied this by this. So there's a reason why I did that. If t2 is greater than t1, the way we can think of it, according to the definition of x, I'm going to draw it over here. X is equal to, so x of t1 is n 0 to t1. So t1 is over here, right? That's one. This is one interval here. Now this interval is from t1 to t2. So according to the definition of the Poisson process, because these two intervals don't overlap, we can they're independent, so we can separate them. So we can write expected value of x of t1, expected value of, I put an extra parentheses for no reason, I don't know why I did that. Just ignore that. So I did two steps in one step here. So first, because this is a sum, I can do expected value of this plus expected value of that. And then I further broke this down because we showed that they're independent because they don't overlap, these regions. So we can write this. So we know from part A, this is just lambda t1. This is just it's a sum, so we can write lambda t2 minus lambda t1, because I can break it up into this expected value minus this expected value. And now we have this. So we need to find expected value of x squared. So we're going to do a little bit of an aside here. So using a similar method to what we did before, we're going to do e to the alpha is equal to, now we're just picking up after the first derivative, right? So when we did the first derivative, we ended up with something like this, right? 1 over alpha. Let me just make sure. Right. So the first, I'm just going to rewrite the first derivative. I don't want to skip too many steps. So this is what we were left with after, wait a second. No, let's start over. It's bad if you try to skip too many steps. Okay. It's just alpha k over k factorial. So k goes from 0 to infinity. Now remember, alpha is equal to lambda t. So first derivative, we get e to the alpha, this because we're taking a derivative with respect to alpha. Here we get k alpha k minus 1 over k factorial. Now again, because we have the k here, k equals 0, we just get the first term being 0, so we can rewrite this as k goes from 1 to infinity. So now we take another derivative. This is still e to the alpha equals, so then we have k times k minus 1 alpha k minus 2 over this. So we get, and it's the same thing. So what we can do, we can rewrite this as 1 over alpha squared, and I'm going to distribute here. So we're going to get sum k squared alpha k over k factorial minus 1 over alpha squared here, k alpha k over k factorial. Okay. Okay. So we have this. Now, what I'm going to do is I'm going to take the alpha squared, multiply on and bring it on this side, and take this guy, the exponential, and bring it on that side. So what I'm going to get alpha squared equals, I get k squared e to the minus alpha k over k factorial. That's all supposed to be in there. K 0 to right 1 minus, and then we have here k e to the minus alpha k over k factorial, k equals 1 to infinity. This guy is just the expected value of x, so this just becomes lambda t, and alpha is lambda t, so alpha squared becomes lambda t everything squared. I'm going to bring this guy to the other side, and I'm left with this summation, which is just the expected value of x squared. Which is expected value of x squared. Okay, so now we can use that. So we're going back to what we had for, so we come back from the aside, and now we're going back to finding the autocorrelation. So what was the autocorrelation so far? We have this, lambda t1, lambda t2 minus lambda t1 plus expected value of x squared, which is just this guy. It is, this is t1. So we have a lambda squared t1 squared plus lambda t1. So let's open this up. We have lambda squared t1 t2 minus lambda squared t1 squared plus lambda squared t1 squared plus lambda t1. Cancel these, and we are left with lambda t1 lambda t2 plus 1. Now remember, this is only for the case that I can actually rewrite this like this, and this will be more illustrative. Lambda t1 t2 lambda plus t1. This is for the case that t2 is greater than t1. Now we have to also consider the case that t2 is less than t1. So then, in order to use this whole thing about them being independent, if t, so this is t1 and this is t2 now, because we have that. So we have to do x of t2 is now independent of x of t1 minus t2. So we basically have to switch this to t2, this to t1, this to t2, this to t2. So doing that, and coming back to the autocorrelation of that, we get r of t1, t2. If you do the whole thing again, you get lambda t2, because we're just changing the t1 to t2 and t2 to t1. We get lambda t2, lambda t1 minus lambda t2 plus lambda t2, these are squared, plus lambda t2. So we open up, lambda squared t2 t1 minus lambda squared t2 squared plus lambda squared t2 squared plus lambda t2. These go away, and we can pull out the lambda. So we have lambda t1 t2 times lambda plus t2. So this is for one case, this is for the other case. So we can write it in a more compact form as this is just, now this is for any T1, T2. We can say it's lambda T1, T2 times lambda plus, and now let's notice, when T1 was less than T2, this piece was T1. When T2 was less than T1, it's T2. So this, we can write it as the min of T1, T2. So let's just quickly analyze this. When T1 is less than T2, we get this equation, right? So the min will just become T1, so we get exactly this. When T2 is less than T1, the min of this is T2, so we're just left with exactly this. So that, it takes care of both situations, and that completes part B and the problem.